Okay, so Cartesian claim that this thing has a uniformly convergent subsequence. Okay. Okay. So so we start off with the following fact. This was actually in your homework some time ago when we were talking about density. So okay. So we had the following result that so this was a homework problem. If K is compact, then there exists a countable dense subset. Okay, so this was one of the homework problems from a long time ago. So this is compact in some you've got a compact metric space, then there exists a countable dense subset, which we're going to call E. Okay, so that tells us that there are these points that are dense in K and that they're countable. Okay, they're countable. It's at this point that we pull out the theorem that we had last time, which was getting a pointwise convergent subsequence on a countable set. Remember that? That's the thing that I call weak. I insulted it, but actually we need it today. Sorry. I apologize. Okay. So by the theorem from last time, which was 7.23, if you wanted to look it up, we know that there exists a pointwise convergent so there exists a subsequence S of n k that is pointwise convergent on E. Okay. And we're going to claim that, in fact, these guys are uniformly convergent. Okay. Okay. So the way this goes is we say, okay, well, right. What do we want? We want to find, given an epsilon, we want to find a k past which these guys are within epsilon of each other, right? So we say, okay, fix epsilon, and then use so by equicontinuity, we know there exists a delta corresponding to that epsilon. There exists a delta such that, if the points are less than delta from each other, then fnkx minus fnky is smaller than epsilon and 3 from each other. Okay. As before, we're going to cover K with epsilon neighborhoods. I'm sorry, delta neighborhoods. Okay. We do something similar to what we did last time. Right. We cover it with these guys, and then there exists a finite subcover. And m delta xi from I equals 1 to p. Okay, actually, let me fix this up a little bit. We're actually going to do the following. We cover K with neighborhoods that are centered on the points of E. Okay, so the E are in our dense set, right? The E is our dense set here. And so we cover every one of these points with a delta neighborhood. Okay. Okay. So then our finite subcover is centered on points, a finite number of points in E. So E1 through EP. Okay, so remember E is where the sequence converged pointwise, right? So by pointwise convergence of the Fnk on E, we know that there exists an n such that for E1 through EP, Fnk EI minus Fnk FNL EI is less than epsilon over 3. Right? As long as K and L are bigger than N. Okay, right? Because we have pointwise convergence, right? At each one of these points, we've got pointwise convergence, right? And so we can choose an n, right? For each one of these, we can choose an n that works, and we take the maximum of all those n's, right? We take the maximum of all those n's, and that n will work for all of these points. Okay. Okay. So right? But now we're basically done. We're basically done because remember we're trying to show uniform convergence, right? Well, uniform convergence means that we want to find an n so that these guys are within epsilon of each other on the whole set, right? And what we've done is show that these guys are within each other at those finite centers of points, centers of the disks. Okay, but equicontinuity will allow us to get points that are nearby, just like in the previous case. Okay, so we say, okay, well, what happens if x is not in there, right? X is a different point. So for x, just an arbitrary x in the set. If k and l are bigger than n, same sort of triangle inequality argument. Fnkx minus Fnlx is controlled by. We just try to find some nearby. This is controlled by Fnkx minus Fnk EI plus Fnk EI minus minus FNL EI plus FNL EI minus FNLX. Right. where x lies in the delta neighborhood of this EI. So you choose the EI that is close by to x, right? Right? And you say, okay, well, by equicontinuity, this thing is smaller than epsilon over 3, and this thing is smaller than epsilon over 3. Right? Because the delta works for this function, and it also works for this function, right? And this is smaller than epsilon over 3. This is smaller than epsilon over 3 because we're past n, right? Because of our pointwise convergence, right? So this is smaller than epsilon 3 because of pointwise convergence. Okay, so that's the end of the proof. Okay. Any questions? Any questions? Let me see if I can say it more coherently. Right, we're trying to show these guys are uniformly convergent. In other words, right, for a fixed epsilon, we want the n so that k and l being bigger than n ensures that fnk x minus fnl x is smaller than epsilon. Right? That's what we want. We want the n that makes these guys close to each other. Okay. Right? By equicontinuity, we can choose a delta so that that all of the functions don't vary by more than epsilon over 3, as long as they're within delta of each other. We cover the dense set, and this is the key part, right? This is where the compactness comes in. We have this dense subset. We cover every point of the dense subset with the delta neighborhoods from equicontinuity. Okay. There exists a finite subcover by compactness. Okay. Right? Then we say, well, look, on the centers of that finite subcover, we've got pointwise convergence. Right? There's only finitely many of them. There's only finitely many points, so we've got uniform convergence. Right? We can find an n that works. For all of these points because there's only finitely many points. Right? We've got pointwise convergence on finitely many points. So we've got uniform convergence on this finite set. Okay, that makes sense, right? We've got an n so that this thing is smaller than epsilon over 3 for E1 to the EP. Right? But every point in the set is close to one of these things, close enough that by equicontinuity we can see that the difference between the values at those nearby points is controlled by the difference in the values at those center points, right? And so that gives us uniform convergence on the whole set. I think that's about as clear as I can make it. You guys okay? Okay, so that was, like I said, that's kind of one of the peak, at least it's the climax of this chapter. Later, I looked online for like applications of Ascoli Arzela, and I found a slideshow called Ascoli Arzela and the Meaning of Life. I'll send that to you later. I think the title is kind of misleading, but okay. Okay. I think so. The last thing I want to do in this chapter is the theorem of Stone-Weierstrass. So there's a theorem called the Stone-Weierstrass theorem, which which says the following: that if you have if f is a continuous function on a closed interval AB, then in fact there exists a sequence of polynomials, P sub n, that converge uniformly to f. Okay, so this is pretty cool, right? It says that polynomials are dense, right? Polynomials are dense with respect to the sup norm metric in the space of continuous functions, right? They can always find whatever continuous function you have. There's always a sequence of polynomials that will give you that will converge uniformly to that function. So this is basically a density, kind of a density result, whereas the previous Ascoli Arzela is a compactness result. This is not only a cool result, but also it's something that uses a technique that is really important. So-called approximate identities. The method of approximate identities. In another book, I've seen them called good kernels. The method of good kernels. Okay, I think the first one sounds a little bit more formal, but the second is accurate because they are good kernels. So you create these things called kernels that are sort of like an approximation of the Dirac delta function. Have you heard of the Dirac delta function? Okay, so yeah, so you create something that basically behaves in the limit like the Dirac delta function. Okay, and then you recover your function via something called convolving. So you convolve with the kernel, and then get a sequence of things that approximate your function. Okay. I don't think I want to get started on it at this point. There's only 5 minutes left. It would be kind of silly to start this big new theorem at this point. So that's it for today. So yeah, and so we have, I think, 3 more lectures left. So next time we'll do Stone-Weierstrass, and then after that we'll do some selected topics in chapter 8. Yeah, so we'll do a little bit on power series and a little bit on Fourier series, a subject close to my heart. Okay, see you guys next time. Sorry, what?